Hello and welcome to my individual contributions video regarding the Game Studio One Project 3, for which I am a part of Team 3, aka the six-piece nuggets with myself, Gabrielle, Neil, Mark, Elliot, and Lewis. So I'm just going to be going over the individual contributions that I've made to the project overall. So let's dive in. So, first, when dealing with the gameplay itself, we noticed a flaw with the nav meshes. And the fact is, if you went anywhere within a nav mesh, all of the AI would come after you, no matter what nav mesh you're in. So right now we see that there is a nav mesh here, but if there was two separate ones, initially the code for the AI was to know where the player's location is at all times. And so that wasn't really going to work because what ended up happening was throughout the levels, whenever we would place enemies, they would all essentially clump at the doorways, just trying to maneuver and get to where the player was at all times. So, because of that, I had to put off any implementations of other power-ups and different features and decided to go with an AI behavior tree. So I had to develop a little bit of a different AI controller. So right now within begin play, we essentially go through and check to see if our BT enemy character is valid. We then run our behavior tree. Now, what our behavior tree is our BT enemy character, and we can find that here. So this is the simple behavior tree that we have. We needed a blackboard as well. So the blackboard value is over here, and we had several keys. We had the self actor, the player's location, start location, last known player location, the player itself, and whether or not they could see the player. So at the beginning, we have a selector. And so this will basically call each of these segments and will stop as soon as one of these fail. So initially, all of the robots will check to see if they can see the player. If they cannot, they will chase. If they can, they will chase the player and move towards the player object. So before it was just the player location, but I decided to just pass in the actual player object instead. That way it was more of an accurate following. That way they could update it at real time. As well, this was an observed blackboard value that would constantly be uh, refreshed. They would go through, move to its last known player location, and then clear that location. Wait a few seconds, and then because this is cleared, this blackboard decorator node would return false, and then they would move back to their start location. So how this is implemented inside the AI controller is after the behavior tree is run at the start, we can now set these key values. So getting ourselves being the enemy, we get the actor location, and initially, because this is at begin play, this is where the start location will be set. So moving down, we go to our player character, and every tick, we check to see if we're within line of sight. Now, we didn't want the line of sight to be so far. So because of this, we added like a sight radius. And so right now it's just set at this arbitrary number. We thought it was proved useful when playtesting. So right now it's set to 21, 21. We essentially compare the two locations right now. The actor's location of the player character versus where our pawn currently is. And if it's within this, we then evaluate the true. And then we can set the key of can see player, as well as the actual player itself and the last known location. So we set the last known location to where the player character currently is. And since this is happening every tick, we will check to see whether or not we can see the player. As soon as this evaluates to false, aka we get out of range, or we can no longer see the player, or get line of sight to, rather, we will then clear the value of can see player. So that will directly influence this behavior tree. So I'll just show that out in action here. So right now, he's following me. And, you know, he's keeping up a good pace. But as soon as, hold on. As soon as he gets to the last known player location, he goes back to start location. Now, we can see this actually happen in the graph. So he's gonna see me go here. He's gonna check to see that he can see us, and he moves back to his start location because these two are now set. So if I quickly go through and show this, we can see that right now if we switched over, he would be moving to can see. Right now we died. But he is investigated, he's moving to my last location, and now that we're here, we can possess, you can see, we go through, if we lose him around this block, we see that he has waited and then he moves back. So that's essentially allows us to play hide and seek with our AI, but mainly it was just so that we could place AI throughout the level and not have them all clump through the doors, because these maps would be massive and we would intersperse these enemies throughout, and it was a big problem when trying to plan levels out like this. And the fact of maybe making spawners that would have these enemies possibly go on top of objects, things like that, it was nicer just to plan everything out manually. So that is the AI controller in a nutshell. So that's the behavior tree, the AI controller, as well as the Blackboard that's associated. And for this, we had to create our own task as well. So this was just a simple task within the behavior tree, which once it receives an execution, we just clear the value of the Blackboard component and finish execute. So that's as simple as that. And you can see that it's being used. This is clear last known player location. We have our name, last known player location, which is the set value. We clear that value, finish execution. So the next contribution within the group would be that of the camera pan system. So this is done with the inputs of Q and E, as well as having the left and right triggers be bound. So first thing was to actually bind the inputs. So that was simple within the project settings. But now when we rotate, we are able to shoot in the proper direction and pan the camera. So this was a nice added feature, just to be able to traverse levels. Although we did have the added functionality of the see-through objects, it was nice to be able to actually experience the artist's levels and pan the camera to be able to look at all the assets that they had. So being able to walk through and see the level through all angles was just a nice feature for gameplay itself. So although we were limited in terms of the twin stick, this was a solution that still kept true to the original control system, but allowed for more dynamic gameplay from the player. So how this was implemented was within the hero itself. So initially we pan the camera left and right, and this is simply done just with the input actions. Again, within the project settings, within input, we can see that it's bound to E, Q, left, right trigger. So we grab the spring arm component, and based upon the input pressed, we either add 90 or negative 90 to its current world rotation. And then we set that. So that's simple enough. And the fun part comes with setting new movement and rotation values for the player. So let's dive right into that. We have our character starting off here, which is with our input axis for move up. So this is the up and down arrows, or along the y-axis on the left thumbstick. And so these are all based on conditions of where the camera angle currently is. So either at 0, 90, the absolute value of 180, because sometimes during testing it would reside in negative 180 or 180. So absolute value resolves this, and negative 90. So at every angle is a condition that is met, and at the certain angle, we simply add the world direction to the player. So it's either an x value of 1, a y value of 1, an x value of negative 1, or the y value of negative 1. So all orientated based on the current camera's rotation. Similarly, with the move right, it's the exact same code, but instead orientated along the x-axis for the left thumbstick or the left and right arrows for the keyboard. And again, 1, negative 1, negative 1, and 1 for the respective x and y values. Now here's where the fun part comes in. Kyle saved the day. Yes, this was a pain to do because of this one node, actually, we found out was the problem, was the decrement, which actually set the value accidentally, and that is not what we want. So the actual macro would set the value, and it would cause so much problems, but luckily we fixed this. So how did this work? Well, first we're gonna go and look at both the input axis for the look up and look right values. So this is all done within the right thumbstick. And sorry if I misinformed you before, the movement was actually with the WASD keys, and the arrow keys are actually for this, which is the character's shooting and rotating aspects. So we grab both of these values and immediately set them to variables. And from here, this is where we get our similar spring arm Boolean checks, which will switch based on the same camera angle. Now, this is where the fun part begins. For each of these, we had to calculate a separate vector. So if we go straight into the 0 degrees. I created macros to do each of these. So it's just the same code as before. We grab in the values for both the right and up axis values, make a vector. We, from that, check its length and see if it's sufficient enough within the joystick to actually warrant a response. And if so, we have this right now set to 0.3. We then set that as a return value. As well, from this, we get a rotation from the x vector, and that is what's going to actually set our character's rotation. So I've created a macro for calculating each of the vectors. And so for some of them, you can see that we've had to use something known as the either negate vector to make sure that the values were properly functioning, or we've had to make sure that we invert the rotator so that we can properly get our counterclockwise rotation in. As without this, sometimes when the camera would pan, the rotation would actually be set in a counterclockwise rotation rather than clockwise, which is not what we want. So then afterwards, we move on to rotate or not, which is another macro that I've created. And so what this does is it takes in the vector big enough condition. If it evaluates true, we then check to see if our character is dead. If that is also true, that is when we set our control rotation. So only then will we do that. And so this prevents us from rotating and shooting while we're dead. And other than that, we will then grab our rotation and set it. So if it is false, we actually get an executable pin here. So found out that you can actually set exec variables as outputs, which is very, very useful because we were able to then from here go through, and then if it is set, input a delay and pull the trigger. Otherwise, if it's not set, we immediately release the trigger, which is awesome. So all in all, that was a big hurdle, but it was a nice quality of life feature for the game, which was the rotation. So next is the weapon system. So inside here, we've created these 3 pickups. Now we have the burst shot, we have the damage boost, and we have the Gravlock. Now the Gravlock is in purple because its full implementation was not where I wanted it to be. Currently, if we play, let me just kill this. Actually, I'll just grab. Currently, if we play, if we activate it, it just spawns these giant orbs. And so that is not really ready for full implementation, but what is the damage boost. So after picking these up, as you can see the nice HUD elements, you can see in the bottom left the widget when it's activated. So for damage boost, as you've seen before, we have the one-shot kill, which is great. As well, we have the burst shot, which is a notable contribution, which took a little bit of figuring out to get. So let's dive into how that was implemented. So with the power-ups, we essentially just have the blueprint for each of them. I added the emissive lights. The assets were provided by Lewis, but we have just your rotating movement component along with some lights just to look like pickups. So that is essentially the same for all of the power-ups. So within the event graph, we essentially just take the side hero, say that the burst shot is equipped. We then show the burst shot HUD widget. So this is directly tied to the widget, which I've made custom events for each power-up. And then it just shows the widget visibility on pickup. So if we then go back to the burst shot, we toggle the static. We basically toggle the power-ups visibility on the map and allow its collision to be set to no collision so that we can walk over it afterwards. We play the pickup sound that is used for all the pickups, such as the key cards, things like that. And we add the notification. This was an addition that was added by Gabriel. And this is just some optional code that allows the power-up to respawn. So that is if we wanted that to be how it was implemented, but we wanted it to be a one-time pickup. So within Side Hero, we have our input bindings, which on controller is the D-pad. And so we check to see if our laser rifle is in a current weapon state. Well, for that, we had to, instead of dealing with booleans, I thought it would be much cleaner to deal with enums. So I've created a enum enumerator just of weapon state, which holds default, burst shot, damage boost, and grav lock. And so this was an investigation that I wanted to go under. So I thought that it was worth doing, and it turns out it is awesome because you were able to really access this enum across a lot of blueprints, which is great. So from the laser rifle, we can check the weapon state, and basically, if it's equal to default, essentially meaning that we cannot override power-ups once they're active, we have to wait for default to be the state again. That is when we can activate the power-up specific events. So if we go to burst shot, which the logic for all three of these are the same. So if we go to the burst shot, we set the enum value to burst shot. We then reset the timer of laser rifle. What this does is essentially inside of laser rifle go through, we switch on the weapon state. So depending on what it is, in our case burst shot, if we continue following along, it is set to 2.4 shots fired per second. And then we clear and invalidate the fire timer so that we can then use that new found shots fired per second value as the timer, which is the same code from the project number 2. As well, we can fire based on weapon state, and this just spawns power-up specific sound effects as well. Now, this is where the math comes in. You can see when using the burst shot that it essentially goes in a radius. And so this was done, and I'm pretty proud of this. The calculations for the bullets are done within a spread here. And so essentially if burst shot is activated, we have a set number of shots. Right now it's 8. It used to be something crazy like 50. And we go through and we set the shotgun spread angle. So this is just the radius of the circle. We go through and then we get a random point in circle, which is our function that we created in order to get a random point in a circle. We calculate the x and y value based upon the cos and sine values of our angle and the distance from the center of our circle. And so we essentially can return an X and Y point that, when used, can then be made into a 2D vector. And from this vector, we're able to get the initial projectile spawn point and, grab the initial forward vector, the right vector, and the up vector, add them all together in order to find and form the end point for our laser shot to travel. And essentially, from the start position to the end position is where we can calculate the distance, grab the, or rather the magnitude, and from that, we can grab the direction and point our projectile in that direction, and thus you can see why it's being sprayed out in a cone. So we spawn the actor and make that projectile transform change. So that's pretty cool. You just basically, for each number of shots, go through, pick a random point in the radius of the circle, and the projectile will travel in the direction of where the laser's endpoint is. So this took a lot of time figuring out, along with some helpful resources, but it's a pretty sweet implementation to a shotgun burst shot at the end of the day. So that is the burst shot. If we go in now to our effect health, we can see help Gabrielle keep track of the lives here. And this essentially just makes sure that our character only has 3 lives. Once it reaches 0, we evaluate to false and we show the lose screen. Otherwise, we respawn our player as per usual. So speaking of these screens, I will show you what happens when we die 3 times. So you can see the health bar at the top. That was actually a vector or a texture that Lewis made, and I had to figure out how to actually make the progress bar fill that image. So that was a challenge in itself, but eventually found a solution on how to do it, which I can show. So once we die, we are deceased. And we've programmed it so that once we die, you actually respawn back at the main factory level. So essentially the start of the game. So we can go into the GUI now and just check out some of the stuff we've done. So within the twin stick HUD, this is where we implemented our D-pads. So right now there are enabled icons as well as disabled icons. And so right now all the enabled opacities are set to 0, as well as we have the keycard icon or the augment chip icons here. And the health bar, which took some time to actually get properly positioned on screen, mind you. So within the progress bar, the way that we got it to actually fill this image was by providing the texture image that Lewis provided, and then getting a fill image of itself as well. And then from there, being able to use that as the progress bar. So this was all found under style, which was something cool that I learned. So this is the HUD that was implemented, as well as some of the functionality. So I had to make a toggle life function for each of the ticks, and essentially we just take a cast to the BP twin stick mode, go through and check to see what the number of lives are at, whether or not it is 3, 2, or 1, and set that value of the widget to hidden, just to let the player know that they have lost a life. Additionally, we have the player lose screen that we quickly created and animated with a quick fade, as well as the intro sequence that we have used and faded. Additionally, within the end credits, I helped to reformat this so that we could have our end credits show within the graph. I helped implement the actual change. This was the old code, but I helped implement this new code. And essentially, right now, the hero character is checked out by Gab, so I can't actually go to the intro sequence level without showing you. But essentially, this is the exact same code, which was used to help with the intro sequence, but instead with the end sequence. And that is by using a play animation with finished event. And so right at the beginning, instead of being called here, we just have it being called inside the begin play event. So it's a little bit different implementation, but this is within the construct event inside our end sequence. So a little bit difference of style, but that's all right. So we just go through and we go through each animation and we make sure that it's only connected once it's finished. And after that, we quit the game. So after the end screen is done, the end credits are done, the player finishes the game, it quits. So that is another implementation contribution that I helped with. Within the pickups, I helped make a health pack. So we have the same pickup toggling visibility happening, along with implementing the static mesh and glow to make it look nice and shiny. Aha, here it is. So we had some emissive light coming from here that we messed around with. But the actual implementation itself is inside the base character class itself. So quickly inside the base character CPP, this is the quick health pack functionality that we added, which was just to make sure that we cannot exceed the current health. So we just add the delta to the health, and we just ensure that we cannot not go over 100. So calculate health plus equals delta. We had to ensure that we could not exceed it. So we always add 50. So if it's greater than 100, we had to simply set it to 100. So it's very, very simple code, but it needed to be added. So that happened internally, and that is the health pack implementation. We had to make sure that the player respawned at the start of each respective level. That was done within each level's level blueprint. So at begin play, we get the player's transform and the game mode, and we set that immediately as the player spawn transform, so that whenever they want to respawn, they will be spawned there. Other contributions were within the enemy character. And so we had to make sure that the punching was set for the animation. And so how this worked inside the animation, we had to have our blend space tweaked inside our ABP. And so if we go to the anim graph, we have play cyborg punch. Now that is done through here by setting a B punching rule. And basically that was tracked as you saw inside SybEnemy. And if that transition rule is true or false, we then just go and do this punch animation, which we had to tweak a little bit with the play rate and the start position just to get it right. So those are the main contributions that I made to the project. I am very excited to work with teams in the future and excited for the next iteration of Game Studio. So thank you very much for watching.